First of all, I want to thank the organizers for inviting me because of the next thing that I want to say. So the big disclaimer here is that I don't know anything about groups. So this is a talk which is like fake it till you make it. But anyway, okay, so I will now inject some dynamics into the picture. It's a survey talk. I'm in no rush to get anywhere. So if you stop me with questions, that's totally fine. And I actually will appreciate that. Okay, so let me start trying to explain a little bit of the title here. So this is supposed to be a schematic picture of what happens when you try to do random walks in a hyperbolic space, so chromo-hyperbolic space. So this is just a schematic picture. This is an actual picture in the hyperbolic plane, but think of it as a schematic picture. So what happened? What is a random walk? A random walk is basically you're taking steps inside the space where each step is independent of the previous one, and you're deciding somehow by some random distribution how you will take the step. Okay? So you will notice from the picture what happens is that sample paths, so this is some random path that is generated by this walk, they drift. So that means that the distance from the starting point of the sample path increases linearly in the number of steps. So you kind of go some steps, and as you make you start somewhere, you kind of do all sorts of random stuff, but as you see, your distance from the initial point increases linearly in the number of steps. And one heuristic of how to explain this is to say that, look, if I start off a sample path somewhere, and if it makes progress in hyperbolic space, then in the hyperbolic space, it's the only way to get back close to the starting point is to backtrack all the way. In hyperbolic space, backtracking is usually very, very hard. So there is more opportunity, or the chances of moving forward are much higher than backtracking from where you came. As a result, there is this drift and in fact, even convergence to the bound. Okay, so that's roughly the heuristic of how this works. I'll give precise definition of the random walk in the next slides. Is that okay? Yeah. All right, just for more information, you want to see cool pictures, you can also see Danny Caligari's website blog, where he draws pictures of random turtles. Blog in the hyperbolic plane. Okay. Now I have to introduce the next object, which is Fuchsian groups. So here is some basic preliminaries. H is the hyperbolic plane. We know that the isometry group of the hyperbolic plane, there should be a P in front of everything, but we are going to forget P's in this talk. So it's SL2R. We'll call a discrete subgroup of SL2R. This is a Lie group. We'll call a discrete subgroup of this Lie group a Fuchsian group. I will be more interested in lattices, so which means that I'm considering Fuchsian groups such that the quotient of SL2R by the Fuchsian group has finite volume. Okay? And then the lattices come in two types, uniform or non-uniform. Uniform lattices means that the quotient is compact. The quotient of the hyperbolic plane, well, forget the rotation factor, just go down into H. The quotient of the hyperbolic plane by the action of the group is a compact hyperbolic surface or orbifold. And non-uniform if the quotient still has finite area, but is non-compact. So that means that the quotient will have cusps. Okay, so that's Fuchsian groups. Now I want to do random walks on Fuchsian groups. So what does that mean? You fix a probability distribution on your Fuchsian group, on your gamma. And what do we mean by a sample path of length n? Well, you create a random product of elements in your group, so G1 through Gn, where each Gi is sampled by this distribution. So this is what I mean. You go around looking for the first group element G1, you use your distribution, that is some probability, you pick this group element, okay? Then you do the next one by the same process, and then you multiply them together. And then the third one, and so on. Okay, so we are in the geometric group theory setting. So one example of a random walk is to take the Cayley graph. And so Cayley graph is now a graph, and now you just go to the nearest neighbor. So it's sometimes called a simple random walk. Which is go to the nearest neighbor. Okay, so that's how, is this clear how we're getting random walks on our groups? All right, so now remember our group has a really nice action in hyperbolic space. So I can project my sample paths using the action into hyperbolic space. So I fix some base point, I generate this sample path up to n steps, and I act on this base point, and I move somewhere. And what happens is that as n goes to infinity, for almost every infinite sample path you generate, you see this phenomena that I showed in the first slide, is that you drift off towards infinity and actually converge to a point in infinity. Okay, so for almost every sample path, this sequence of points that we get converges to the boundary at infinity, which is the circle in this case. Okay? So once you have this convergence, you can define the measure on the circle. The stationary measure is precisely the measure that gives you the distribution of these points that you get from these sample paths. So these sample paths are limiting to the circle. They are distributed along the circle in a certain way. The distribution is exactly this stationary measure that captures this distribution. Okay, so it's what's the probability of a subset A of S1 is the probability that an infinite sample path converges into this set A. And it has this additional property called stationarity, which means that the measure that you get on the circle, this measure A, this measure nu, so nu of A is the mu average. So mu is the initial distribution you put on the group. It's the mu average of the translates of A. Okay, that's the stationarity property. And in fact, it turns out this measure is the weak limit of the push forwards of the measure, where mu of n is the n-fold convolution. Just for clarity, well, what is mu of this? Well, this is the sum over h, mu of h inverse, well, I never get this right, but something like this. Is the probability that you get to the group element G in 2 steps. Okay, that's mu, that's the second convolution of mu. And then you'd keep convolving with itself till you get mu n, and then the weak limit of these mu n's pushed forward into hyperbolic space will eventually give me this measure on the circle. Okay? Everyone happy with that? Yeah.
So did you say that
yeah. So one has to make sense of what almost every means. You basically passing from finite paths to infinite paths. So there is a measure on the infinite path space, and then you're, with respect to that measure, almost every path converges to the boundary. Okay? All right. So now you have this measure on the circle at infinity, and you can ask the following questions. Well, what happens when you compare this measure to the Lebesgue measure on the circle? So the precursor of this is work of Furstenberg from the 60s, where he showed that for any lattice in SL2R, and this is in fact any lattice in any Lie group, but for any lattice in SL2R, there exists a distribution on the group such that the associated stationary measure at infinity, which you're doing these random walks and getting this measure at infinity, this is absolutely continuous with respect to the Lebesgue measure. And this theorem of Furstenberg's is the beginning of what is called rigidity theory for lattices in Lie groups. Okay, this was the first, for example, you can use this idea to prove that a group that can arise as a lattice in, say, SL2R cannot arise as a lattice in SLNR, where n is bigger than 2. Yeah. There is a random walk on the group that gives you an absolutely continuous measure at infinity. It is usually supported on, it is that the random walk arises from discretizing the Brownian motion in the hyperbolic plane. So it's usually is diffuse support, so it's supported on the whole group. There is a non-zero probability of doing a really large jump in one step. Yeah. And in fact, it will, to just add more detail for your, so the resulting measure that you get will have finite first moment with respect to the hyperbolic metric on the group. So take the hyperbolic metric, take the orbit map, use the orbit map to get a hyperbolic metric on the group, not the word metric. And with respect to that one, this will have finite first moment. If it's a co-compact group, then they are quasi-isometric, so it's the same statement. But if non-co-compact, that's a different statement. Okay, any more questions? Yes. It is the Poisson boundary. I'm talking about, so we are taking a particular geometric model for the Poisson boundary. We are saying that the circle is the Poisson boundary is an abstract measure space, and the circle with the stationary measure is specific geometric model for the Poisson boundary. Yes, that's Furstenberg's work from 60s. In that case, the replacement for S1 is what is called a flag space of full flags. So now imagine you are in SLDR and you're doing random matrix products in SLDR. Then you know that for almost every sample path, you will have the matrices that you get will have singular values. Those singular values are what are called Lyapunov exponents. Those Lyapunov exponents will be simple, and corresponding to the Lyapunov exponents, there will be subspaces, Lyapunov subspaces. Those subspaces will form a full flag, and that's where you converge. Okay? So that's in SL2R, you are actually getting the subspaces. Remember, matrices in SL2R, their Lyapunov exponents will come in pairs, lambda inverse, etc. And the directional part of it, so that's the rate of drift to infinity, which is the Lyapunov exponent for this matrix. And the point that you converge at infinity is the directional part. It will correspond to think of the circle at infinity as projective space. Okay, that's where you converge. Yeah. I don't want, that's getting a little too technical, so can I skip that and I'll tell you later. Okay. Right. So moving on to is that okay? Yeah. So yes.
So can you give an example for most distributions? It's singular. Can you give an example of where it is absolutely?
So the Furstenberg measure is non-constructive. So we don't really know, it's taking Brownian motion in the plane and trying to discretize that. So if you ask me, well, what is the probability from moving from this group element to that one, I can give you an estimate for it, but not really a precise answer.
So it's not as simple as just assigning numbers to...
Yeah, the numbers have to be careful. Basically, it's a limiting process. You're assigning numbers initially, making the measure more and more diffuse to kind of simulate what's happening with the Brownian motion. And then you kind of showing a limiting construction that you do actually get a measure in the limit. Does that make sense? Okay. For non-uniform lattices, in fact, what you can prove is that, so here is one answer to your partial answer to your question. If you take so remember, non-uniform lattice means that it's the quotient is a finite area hyperbolic surface, so it has cusps, so it has, in particular, your group has parabolic elements. So if you take a measure on this group, which has a finite word metric first moment. Okay, so you can fix some generators for this group that defines a word metric on the group, and then this is a moment condition with respect to that. Okay, so roughly speaking, what is that? If you press me to write down the moment condition, it will look something like this. That oh God, let's see. Yeah, something like the probability of jumping to G scaled by the distance in the word metric between identity and G. This should be finite. Okay, that's for first moment, finite first moment. Okay, so if that is true, then the stationary measure that you get is at infinity is singular. This is a theorem of Guivarch and Lejeune from the late 90s, and now there are different proofs in the literature. Lashier, Heisinski, Mathieu, Derwak, Lepsin, Navas, and one proof by us with Mahara and Thiot. Okay, so now in the next slide, I'll try to explain the main idea of why you get singularity in case of non-uniform lattices. And this is a beautiful picture for SL2Z. This is always fun to draw this picture. So what is this picture? This is trying to show you some kind of circle packing that is very natural to SL2Z. So the quotient of SL2Z is the modular surface, and it's very typical to draw the modular surface like this. Right? You might have seen many talks where it's drawn like this. So this here is the cusp at this is here is the cusp. So it's orbifold point infinity. This is 3 and this is 2. Okay? So this is corresponds to, if you take the SL2Z action on the upper half plane, this corresponds to the point I. This corresponds to the third root of I, third root of 1. So that's a point fixed by, this is, point fixed by an order 3 symmetry. Remember, the SL2Z is also Z mod 2, free product Z mod 3, and these are the free fixed points of the finite factors. Okay, and then what we are doing is we are taking a cusp neighborhood and we are taking it as large as we can build it. So the maximal cusp neighborhood in SL2Z, when you draw it, it looks like these horoballs when you lift it to the upper half plane. So you are getting these horoballs centered, sitting over all the rational points. Okay, and then there is this one horoball which is at infinity, and all of these horoballs, this is called a Ford packing, by the way. Okay, and now we have picked some point outside the horoball. Let's say, if my point was in the horoball, I would just shrink the horoballs equivariantly to avoid the point being in the horoball. So with this point, and remember the SL2Z action, so I can call these triangular regions that you get here, these regions that you get here, this triangle here, and all of its equivariant copies. Yeah, that's the thick part of the modular surface. See, okay, and the action of SL2Z on the thick part. So where should I write? I'll just erase something. So I have taken H, I have removed from it all of my horoballs, and I've taken this with the path metric, and the action of SL2Z on this gadget, on this space, is co-compact. So by Swark-Milner, Milner SL2Z is quasi-isometric Qi to this space. Okay, so these blue dots are showing you an orbit, and you can embed the Cayley graph along the blue dots. And essentially, this is quasi-isometric with the path metric to SL2Z. But notice what happens then, that SL2Z, this orbit can never actually go inside the horoballs. So the whole orbit lives in the thick part and actually detours around all the horoballs. Okay, so if we take a piece of the orbit and we go, so notice that in particular, the orbit is quasi-isometric to a trivalent tree. So from this point, go forward, then you have 2 branches, then you have 2 more branches, you have to keep going. This is quasi-isometric to the trivalent tree. So you could ask, well, okay, let's start here and then do, go right in my trivalent tree n times. What's the probability of that in a random walk? In a random walk, imagine you were trying to do a random walk, which is nearest neighbor with respect to going right and left. Well, that's like choosing R out of 2 choices, choosing R n times in a row. So that's exponentially unlikely to do that. Okay, so imagine you have a sample path which does that initially and keeps going forward. Well, it is converging into the interval which goes between 0 over 1 and 1 over n. Its Lebesgue size is 1 over n, which is the probability of doing first, n R's in a row in the Lebesgue measure. But in the stationary measure, the probability is exponentially small. It's 1/2 to the n. So there is this exponential discrepancy between what you see in the Lebesgue measure and what you see in the stationary measure. Does that make sense? The probability that you walk around the horoball n fundamental domains is exponentially small in the stationary measure, but only 1/n in the Lebesgue measure. Yes, you're basically using the fact that the group under the orbit map is exponentially distorted along the parabolics. Okay, so that's the main idea. And that main idea leads us to the following theorems. So now I'm again resorting to stating the theorem in a general non-uniform lattice, and then I'll tell you the specific version of the theorem for SL2Z in terms of continued fractions. Okay, so again, take a hyperbolic geodesic ray from a base point in H. You run along your hyperbolic geodesic ray for time t, and then you ask, well, what is the closest orbit point around to my point gamma t? So this WT here, WT of x is the orbit point that's closest to gamma t. Okay, so that's what is called an approximating group element. You have a hyperbolic ray going through H, and then I'm trying to approximate this hyperbolic ray along the group. Okay, so that's approximating group element, and we have the following two theorems that for stationary measures, the limit of the word length of this approximating group element divided by time along the geodesic, this is finite. Okay, and this is kind of easy to explain heuristically. What happens is that this is a non-amenable group inside which a random walk will always make linear progress, so the word length will grow linearly in the number of steps of the sample path, but so does the hyperbolic distance. Because the group has an nice action on the hyperbolic space. The positive linear drift also holds there. So it's just a ratio of two linear drifts, if you will. Something like that. Okay, so that's finite. It can also be explained from this exponential distribution of cusps of walking around the cusp that I mentioned before. Some kind of finiteness of some expectation value of some random variable. On the other hand, for the Lebesgue measure, the same limit is infinite. So we know that the two measures are singular with respect to each other. So let me give you the specific version of this for SL2Z. What happens for SL2Z? Well, what is this theorem saying directly for SL2Z? For SL2Z, at least the one version of it. Forget about the first part, but for the Lebesgue measure, this is a very familiar statement. For SL2Z, the first one, we rederive essentially the following theorem of Gauss. For Lebesgue, almost every point x in the interval, its continued fraction coefficients So what do I mean by that? You take x and you write it the following way. It's in the unit interval, so I can write it like this. And I'm taking a Lebesgue random point, so it has an infinite continued fraction. So on. And you take these continued fraction coefficients and you compute the following limit. So what is the average of the first n coefficients? So the average coefficient is unbounded. Okay? And this is an easy exercise. If you've seen Brin and Stuck, this is an easy exercise with the Gauss map and the invariant measure for the Gauss map. Okay, so first course in dynamics, do this exercise. Right? You need ergodicity of the Gauss map for the invariant measure, and then this is just an ergodic average of some random variable that the Gauss map is kind of measured. Okay, all right. So this is this statement here is kind of that's it. Any questions? Okay. So now let me change track a little bit and talk about quasi-symmetries. So remember, we are talking about measures on the circle, so it's natural to consider various maps of the circle which arise in analysis. One of them are quasi-symmetries. So what is a quasi-symmetry? A homeomorphism of the circle, which has the property that if I take two intervals which are adjacent, so they share an endpoint and have equal size, and I map them over, then their sizes are not changed too much. So this property here is saying that when I take two intervals of equal size and map them over, look, their size can only change by some uniform factor. This is what is called a quasi-symmetry. And quasi-symmetries arise pretty naturally. For example, if I have a surface and I want to equip the surface with two hyperbolic metrics, two complete hyperbolic metrics. So I'm given a topological surface and I uniformize it in two different ways. Okay? So now I have the surface, I have two different hyperbolic metrics on it. That induces a map between them, between the universal spaces, universal covers of these hyperbolic spaces. So there is a map from hyperbolic plane to the hyperbolic plane, which is pushing this hyperbolic metric to that one. This map is necessarily what is called quasi-conformal. So you are getting a pi1 equivariant quasi-conformal map from the hyperbolic plane to the hyperbolic plane when you want to replace one hyperbolic metric by another. This quasi-conformal is also quasi-isometry if you prefer that language. Now this quasi-conformal map of the hyperbolic plane extends to infinity to go give a homeomorphism of the circle, which is a quasi-symmetry. So quasi-symmetries are quite natural in the world of hyperbolic surfaces. They arise as the traces at infinity of pi1 equivariant quasi-conformal maps on H. Okay? In particular, what happens in this picture that I described is that when you take this quasi-conformal map, take its trace at infinity, you get a quasi-symmetry which necessarily pushes forward the Lebesgue measure to something singular. Okay, so any pi1 equivariant quasi-symmetry at infinity which arises in this way is actually singular. So you could ask, oh, maybe I was looking at the wrong, somehow I was looking in the wrong coordinates. What if I change coordinates by a quasi-symmetry? I might take my stationary measure, which is singular, and make it absolutely continuous. That's the kind of thing you would wonder. And as I said, quasi-symmetries can be singular. They can do all sorts of things. They can promote sets of small Hausdorff dimension to sets of large Hausdorff dimension, etc. Okay? And they arise naturally, not only in this context, but they arise more naturally in lots of topics in analysis. So there's work of Saunier and Pfefferman who are interested in zero measure sets, etc. So there's some analytic background here. Anyway, so related to the question of stationary measures, you can ask, well, can I mess my stationary measure? Can I straighten out my stationary measure by a quasi-symmetry? And so McMahon conjectured that this is not the case. You cannot do this. And we answered McMahon's, well, yeah, this is correct. So the McMahon is usually correct. You cannot straighten the stationary measure by any quasi-symmetry, and I'm not even requiring pi1 equivariance here. Take any quasi-symmetry of the circle, and you try to push forward your stationary measure by the quasi-symmetry, and it remains singular. And what's the main idea of the proof is the following, that quasi-symmetries, remember, they can make you singular, so you can ask, well, how does the Radon, so something becoming singular means that the Radon-Nikodym derivative at almost every point is blowing up. So you could try to understand how quickly how is the Radon-Nikodym derivative blowing up? And this is polynomially for quasi-symmetry. So they only introduced polynomial corrections. But remember on the previous slide, I said that the singularity here is arising from the fact that doing n steps around a horoball is exponentially unlikely in the stationary measure, but only polynomial, 1 over n unlikely in the Lebesgue measure. So the discrepancy here is exponential and not polynomial. So no polynomial corrections can actually rescue you. And that's the main idea of the proof of this theorem, that Okay, there is no version of this theorem in higher dimensions. Quasi-symmetries in higher dimensions are actually absolutely continuous. They can never mess with your Lebesgue measure. And this is the beginning of Mostow rigidity. So one proof of Mostow rigidity is exactly you take your homotopy, you realize it as a quasi-isometry of H3, you take the trace of it at H2, that's a quasi-symmetry or a quasi-conformal map of H2, that's absolutely continuous, you then show that it's actually rigid, it's only a Mobius transformation. Okay, so this is the beginning of Mostow rigidity. So there's no version of this in Hadoop. Okay, now we can ask about, okay, so you had this very nice crutch, which is the parabolic subgroups. What happens when you take uniform lattices? And the answer is that we don't know very little about uniform lattices. So there is a conjecture from the 90s that for any finitely supported distribution on a uniform lattice, the associated stationary measure is singular, on the circle is singular. We have only maybe very little progress towards this. So the first thing I want to mention is work of Kosenko and Tiozzo, where they showed singularity for co-compact lattices, very symmetric ones, like symmetric tessellations of H, and I think simple random walks on such tessellations. So it's a very restricted setup, but they actually showed that the stationary measures are singular. And more soft progress is in my work with all of these other smarter people than me. Aitor Azemar, Sebastian Guzel, Thomas Heitel, Pablo Lessa, and Shilar Ioannik. And here we showed the following. So suppose, remember I have a lattice, which is co-compact. So let's just look at the underlying topological surface, H mod gamma, right? Let's just look at the underlying topological surface. Now, changing the various hyperbolic metrics on an underlying topological surface is parameterized by something called Teichmuller space. The Teichmuller space of S, this space here, is the space of all marked hyperbolic metrics that your given surface can carry. So what we showed is that if I fix an initial distribution on this abstract group, and then I take all of the different points in Teichmuller space that allows me to project my random walks into the hyperbolic plane, a point in Teichmuller space basically gives an action of this group on the hyperbolic plane by a co-compact lattice. So I take, for every point in Teichmuller space now, I will have a corresponding stationary measure. And what we proved is that outside a compact set in Teichmuller space, we do have singularity. Okay? So there is some compact set which we cannot pin down, but outside that, we do have singularity of the stationary measure. And this works by looking at sort of, there's this entropy over drift formula for the Hausdorff dimension of these measures. And basically what we show, so the entropy of the random walk is something intrinsically defined on the group, but the drift of the random walk is using the action of the group on the hyperbolic plane. And we show that basically outside the compact set, this drift becomes too large. Yes? No, it's not. There's no mapping class group here, actually. So, yeah, you're given a distribution on the group. So imagine like you have given the generators of the group and you're doing a simple random walk in these generators. And then K is some compact set outside which you know that one of the generators is very large. It has a large translation length. And we kind of use this to show that forces the drift to be large. You're winning the game by simply changing the marking. Yeah. The generator having a really large translation length means that every time you see the generator in your sample path, you're doing a big jump in hyperbolic plane that's sort of saying that your drift has to be large if the jump aligns with the geodesic that you're tracking. And you have to show basically that this happens quite a lot. Okay, so that's unsatisfactory but partial progress towards the singularity conjecture of Givarch, Kayamanovich Letrappier. But again, we have no control on the compact set. Ideally, what is being conjectured is that the compact set is empty. Okay, so moving on. Let me talk a little bit about what is known beyond Fuchsian groups. So I took isometry group of the hyperbolic plane. You could take isometry group of Hn, where n is bigger than 2. And there we know singularity for oops, sorry, I didn't mean to do that. There we know singularity for non-uniform lattices again. Because again, there are non-uniform lattices in isom Hn are giving you hyperbolic manifolds with finite volume, but non-compact. So they have again cuspidal regions which look like torus cross R. And the torus parabolic subgroup again has the same kind of cuspidal geometry. You have horoballs, etc., etc. So again, your sample paths will stay outside these horoballs, and they will be exponentially distributed for large to see like distance n in the horoball, whereas on the boundary of the horoball. Whereas in the Lebesgue measure, this will now be polynomially distributed rather than 1 over n. So it will be 1 over n to the power d minus 1. Where d is or n minus 1, where n is the dimension. Okay. This makes the statistics required to find singularity harder. So the statistic that we used in this theorem, word metric divided by time, word length of the approximating group element divided by time, this statistics is no longer sufficient in higher n. So they have to do a lot more work, a little bit more work here to actually find the right statistic. Okay, but again, once you set up the statistic, it's like one of those infinity kind of statements, or finite infinity kind of statements. The statistic is finite in one model and infinite in the other. In higher rank, there are examples of singularity produced by Kamenovich and Leib-Prinz, and it's again using this idea of taking the Hausdorff dimension of the limit measure on the flat space and expressing it as some kind of entropy over a suitable expression of Lyapunov exponents. And then again, you make the Lyapunov exponents blow up while keeping the entropy the same. The game is much more difficult in higher rank because of the fact that this is a famous result of Lubotsky, Moses, Raghunathan, that the Riemannian and word metrics in higher rank are quasi-isometric. So you no longer have distorted subgroups anymore. Okay, even when you have parabolics. So you don't have this kind of easy discrepancies to look for, a much more difficult problem in higher. I was a PhD student at Caltech, so that's California Institute of Technology, and where Richard Feynman spent most of his life. And there was a joke in the physics department that if you mention Feynman in your talk, then you get extra points. So now we are in a facility of the Tata Institute. I mentioned Raghunathan in my talk. I should get extra points. Okay, so that's, Raghunathan makes our life harder, okay? What are other contexts in which you can talk about this theory? So mapping class groups. Well, this is where I first started, actually, not the Fuchsian group setup, but mapping class groups are in many ways analogous to Fuchsian groups, and I should give, nobody has defined mapping class groups, so I'll define a mapping class group. So S is a finite type surface. So finite genus, finitely many mark points. So the mapping class group of S is the set of orientation preserving diffeomorphisms of S. And here I'm requiring that the mark points go to mark points modulo isotopy. So if you wish, this is the orbifold fundamental group of MGN. The moduli space of curves of genus G or Riemann surface of genus G with n mark. Again, I've ticked off one box. I've mentioned some algebraic geometry. Okay. So for mapping class groups, you can do a similar story. You can do random walks on the mapping class group. You can use the action on Teichmuller space, which is the universal cover of MGN. You can project the random walk there, and you get some convergence to the boundary. Again, there is some kind of Gromov hyperpolicity phenomena going on here. They are not Gromov hyperpoly spaces, but there is still enough of negative curvature aspects available that the random walk converges to the boundary, you get a measure on the space of projective measured foliations, which is some kind of boundary at infinity for Teichmuller space. And you can prove that for, again, many kinds of initial distributions, you get singular measure at infinity. And recently, Eskin, Mirzakhani, Rafi have given the solution to the Furstenberg problem, which is to create a random walk on the mapping class group that will give you absolutely continuous measure at infinity. And this kind of result should have applications for a certain problem involving Lyapunov exponents for a certain co-cycle built over the Teichmuller flow. But we can do this for all strata by different methods anyway. So yeah, perfect time to stop.
Questions for the speaker?
So you said most of the stationary measures are singular with respect to the Lebesgue measure.
Yeah.
So do you know what about singularity or continuity between various stationary measures? Like for example, if you fix a lattice for various probability distributions.
That's a good question. So one has to first understand how you're changing your measures. So I mean, I'll give you an example of two measures that look different, but will have the same measure at infinity. So take mu as the initial distribution on the group, and now just take mu square, like mu to the second convolution of mu. And their stationary measures are at infinity are identical because mu, the convolution of mu with itself, is not really doing a different random walk. It is doing the same random walk, but just taking 2 steps at a time. So one has to formulate the question correctly. I don't know. Like the main difficulty is would you formulate the question first? And yeah.
Okay, so question would be for fix a lattice.
Yeah.
You have 2 different probability distributions on the lattice, so that the stationary measures are just not absolutely continuous.
That's absolutely true. And the one way you would arrange this, for example, is you could say, let's, for example, play the game in hyperbolic plane. So you have some hyperbolic surface. You can think of the probability distribution as almost kind of assigning a length to a curve. And if I make sure that it's not a stationary measure, but something else which is related called the green metric. If I make sure that the green metrics of these two measures are different, then I can arrange that they are singular at infinity. And this is an easy game to play by just putting very large probability in one direction over another. I don't know. So this is exactly related to this question that the Furstenberg measure is not very explicit. It's coming out of a limiting process, and maybe you can fudge with it a little bit. But I don't know. Like, yeah, that's a good question. I don't know what to say here. I simply don't know the answer. Like, what kind of measures will give you absolutely continuous measures at infinity? I should also say that. Yeah. Sorry. Yes, it is a negative curvature phenomenon that makes it transient. I was trying to say this in the first picture is that it is because of the negative curvature that once the random walk heads in a certain direction, it cannot backtrack easily. You see, if you imagine that instead of this happening in the hyperbolic plane, this was happening on a tree. You did your random walk and you've drifted out somewhere in your tree. Now for the random walk to come back to close to where you started, you would have to, you're in a tree. So you have no choice, you have to exactly backtrack all the moves that you did. Whereas your probability distribution will say, well, backtracking is hard because I have to repeat that exact sequence. Whereas I'm much more likely to do random stuff. That random stuff will keep forcing me to have very small backtrack and keep forcing me going forward. So you are kind of nesting further and further out in the tree, eventually converging to a point at infinity, which is the Cantor set, from a boundary of the tree. Yeah. So this is like the coarsely, like this is the negative curvature aspect that gets used in all of these setups. Yeah. No, because I mean, what does it mean to do a random walk on pi 1 of S2 of Rasa? You're only doing a random walk on Z. A random walk on Z is just recurrent. So there is something to be said related to this question which was asked, which is like if your lattice in higher rank, so you do have flats around, but essentially what happens is that typically you don't continue to stay in the flat. So there is some non-elementary property of the distribution that needs to be satisfied so that, you know, you are supported on, you cannot live in a flat. Basically, your random walk cannot live in a flat. As long as you ensure that you keep stepping out of the flat enough number of times to not have any kind of recurrence property. Okay, so that's, yeah. Does that answer questions? Yeah.
Any more questions? Then let's thank the speaker again.